Hello everybody again. Today I'm going to show you how to analyze an ORCA output file and how to visualize the results in a molecule analyzers called ChemCraft. First we look at the output file in TextPad. I'm going to give an overview. It initially starts with the title of the name of the package and data about the creators of ORCA. Then it gives different flags, that warnings or recommendations for different options that have been used, and then it reproduces the input file. This is quite useful too, because the input and output files are different, so in this way you can always remember what were the specific options that you use for that particular job. I always try to use several comments, although sometimes I forget to update the comments for the particular calculation, but it's important to describe what is the flow chart of the calculation. Where did you start? Did you start from a manually drawn structure? Did you start from a previous calculation? What level of theory you are using? So I am not going to describe all the options that I've been using here, because some of them are very specific to my systems, but I'm going to say that I use the TPSSH functional. It is an advanced, or a, let's say, quite accurate functional for performing density functional theory. It's a hybrid functional that I'm going to talk about in a later video. I perform frequency calculations, in this case with a numerical algorithm, so that allows me to determine thermodynamic properties of this compound. And I calculated using a pseudo solvent, so I embed the molecule in a system that represents dimethylformamide in an approximate way. It represents the polarizability of a solvent, more specifically. There are many other options, and particularly here in the field plots I am also generating a cube file, which is a file that allows us to represent a 3D surface in a format that's called cube. That's an old format from the program Gaussian, but it's a popular format that can be read by many different visualizers. That's why I use it. Then the structure of the geometry, the coordinates of the molecule are listed again. In this case, what I'm calculating is oxidized ferrocin, so the ferrocinium cation that has a charge of +1 and a spin multiplicity of 2, which corresponds to a spin 1/2. So after this, ORCA gives many details about different options that have been included in the calculation. Then it translates the coordinates to something called redundant internal coordinates. That is what by default ORCA uses for geometry optimization. Then I'm going to scroll. There's a lot of information about the basis sets used. These numbers here represent the functions that are used to describe the different atoms in, for example, the different orbitals in, for example, hydrogen and carbon. All these numbers represent a different Gaussian function. Then there's a lot more information. It's a very long file with a lot of information. Here are, for example, the coefficients for the molecular orbitals that have been calculated as a function of the basis orbitals, the orbitals that were defined by the basis set for each atom. These lists of molecular orbitals are quite long, and after this there is other information. So the best way to search for something in an ORCA output file is by using the search function and remembering some keywords in particular. So, for example, the runtime for this calculation was 4 hours and 51 minutes. But if you notice in my input file, I use 16 processes. That means I use 16 cores in a cluster for doing this calculation. So you can imagine that the calculation would not have taken 16 times this number of hours, but it would have taken considerably longer if I had performed that in only one core in one computer. So that has to be taken into account. So for example, if I go and type frequencies with capitals in here to make it easier, I move the cursor until I found this section that's called vibrational frequencies. In here, all the frequencies starting from the first ones are 0. I don't know why there are a few 0 frequencies initially in the list. It's always there. But then I have first a negative frequency and then a series of increasing positive frequencies that go up to 3260 reciprocal centimeters. This negative frequency is labeled as an imaginary mode. That means that there is some vibration of an atom that is not really, doesn't represent an optimum bond distance or bond angle. So that means that the molecule would like to distort. In this case, because of the number of this frequency, which is quite small, around minus 50 wave numbers, this is just a numerical error in the calculation. It is not a real, doesn't have real chemical significance. But in many other cases, this has to be checked, particularly if there are many larger imaginary frequencies. What is the threshold for considering to be significant or not is a matter of discussion. Personally, I consider everything that's more or less below minus 100 wave numbers to be considered just numerical noise, and I don't mind it, except I'm doing something very specific. There's more information. So if we go, for example, we search for single point, we'll see that the final single point energy of this molecule is this number, minus 1650.9, etc. Hartrees. All energies are given in Hartrees unless otherwise explained in the output file. The conversion from Hartree to kilocal per mole or kilojoule per mole can be found. I will put a link to a website called Energy Converter. I don't remember the numbers offhand. Then, after there are many other options. For example, the previous energy was the final single point energy from the first step of the calculation. This is the final single point energy from the end of the calculation after the geometry optimization has been performed. So it says after that optimization run done. After this, there's information about how the cube file was generated for the spin density. There's another information, then the frequency region starts, and at the end we can see that there are a series of corrections of the electronic energy, which is listed here. There are corrections because of 0 point vibrational energy that I will talk about in a future video when I describe the basics of quantum mechanics. Basically, molecules are always vibrating. So there's always a small amount of vibrational energy, even at 0 Kelvin, even in the lowest energy state of the molecule. So that correction is necessary. Then there are thermal vibrational corrections, rotational and translational. Translational is quite important sometimes, particularly when calculating different reactions which involve a difference in number of molecules in the reactants and the products. So the thermal energy is listed. Then the enthalpy correction is calculated. There are equations for that, and there are a series of assumptions that ORCA is making in order to calculate that. So people interested should read several books and papers with reference on how the details of these thermodynamic properties are calculated. But that's for people who want to go deeper into this subject. There are entropy corrections, and then there are finally the calculated Gibbs free enthalpy is listed, which in this case is this value. It's slightly different, slightly lower in this case than the original electronic energy. So depending on the calculation, there can be much more energy, much more information listed. For example, if I go and search for the word loading, there's a loading population analysis that tells us what is the partial charge and spin population that has been estimated for each atom. These numbers, for example, the loading population analysis tells us that the partial charge on iron is 0.01 and the spin population on iron is 1.08, which means that there are more than 1 ampere electrons in total. In the iron, but these numbers have to be taken with a grain of salt. These are approximate numbers because there is no unique way of partitioning the spin density or the total charge into atoms. These are choices how these things are calculated. So it is useful to calculate, to compare different molecules which are in a series, how these numbers change, for example, with some structural variation, with substituents, for example. It can be used qualitatively to understand some things, but these numbers should not be considered to be written in stone. There is much more detailed information on how the charges and spin populations are divided in the different orbitals of each atom. This is a little bit very specific. I don't generally use this information. So now we are going to go to the visualization of the output file in the program ChemCraft. Sorry for it. ChemCraft is a visualization program for molecules and for calculation results, which is actually quite nice. It is not open source. It is proprietary and has to be purchased, but the license is not very expensive. So I have access to a license to this program, and I'm using it now because Avogadro has some problems sometimes and crashes, and ChemCraft does not. And also it has many features which I consider to be better than Avogadro, but that's only my opinion. For example, what we can visualize here in the molecule, this is ferrocinium, the ferrocinium ion. For example, if I visualize one molecule, I see there is the negative frequency implies a rotation in the 2-cyclopentadienyl ligands in respect to a certain axis that involves the iron atom and the center of the ligands. So this was actually a chemically significant frequency, negative frequency, but so it's not due to numerical noise, but it is due to probably that the calculation, because it doesn't have any other molecules, there is a certain freedom of rotation. The chemical signification of this is probably beyond what we want to discuss right now. So I'm going to go, for example, to these frequencies, and you can see that the higher frequencies, around 3200 wave numbers, correspond to CH stretching vibrations. If you have studied infrared spectroscopy, you can see that this makes sense. If you look, for example, you have repeated vibrations because of the symmetry of the molecule. The two cyclopentadienyl ligands are basically equivalent, so you would expect certain vibrations to involve one of the ligands and other similar vibrations to involve the other ligand. For example, these are all different. These are different vibrations. If I go to the lower vibrations, around 1400, these are more complicated modes, but the purpose of this is not to deeply analyze the electronic and geometrical properties of this molecule in particular, but just to show different capabilities of Avogadro. So if we scroll up and go to optimize geometry, here in tools we have the possibility to render molecular orbitals, show molecular orbital energies diagrams, and other properties that would have been calculated by ORCA. So for example, we're going to render molecular orbitals. This dialog box appears that shows us the alpha molecular orbitals listed according to energy, from the lower energy orbital, that's minus 255 Hartree, to something that the orbital 48, which is the last alpha occupied orbital with an energy of minus 0.255 Hartree. Then the beta orbitals will come. So the same, we can see that the last occupied orbital here is 47. So that means that there's an extra electron in an alpha orbital than there is in the beta orbitals, which of course is, we already knew that because the calculation was submitted with a spin multiplicity of 2, which corresponds to 1 ampere electron. So that means, here 48, that means that there's one extra alpha orbital. One extra electron in an alpha orbital. So for example, we are going to plot a few orbitals around the what would be the HOMO-LUMO gap. The HOMO would be orbital number 48 and the LUMO will be orbital number 49. So we are going to plot these 7 orbitals, only the alpha ones, and these are options for low quality versus high quality. So I'm going to go to this intermediate quality and check OK, and it's building the 3-dimensional map. So it's basically generating a grid that allows ChemCraft to plot these orbitals. For that, certain keywords in the ORCA input file had to be included, which I didn't list, which were basically to print basis set information and print molecular orbital coefficients, so that visualization programs can read those data and then draw the orbitals. So for example, if I select one of these orbitals, there are different options. So I'm going to click show isosurface, and both signed, because orbitals basically are 3-dimensional waves and therefore have phase. They have positive regions and negative regions. So when orbitals are plotted, both signs should be considered, but the program allows us to choose. The contour value is a certain value that tells us at which value of the orbital grid we want to cut and draw this surface. So for example, if I put a lower value, 0.01 instead of 0.03, I will get a larger view of the orbital. The orbital is still the same, it's just a visualization that's changing. If I put a larger number, I get a smaller orbital. So 0.03 is a nice default. So if I plot the different orbitals, what I can see clearly is that all these orbitals around the HOMO-LUMO gap are a mixture of metal and ligand orbitals. So for example, we can see here that the LUMO plus 2 orbital is already contains mostly ligand character. But if we go originally to the for example, the LUMO minus 1 orbital is basically would be some type of dxy orbital delocalized and or mixed with ligand orbitals. So for example, if I increase this number, I would see a larger character on the metal. This would be easier to recognize as a metal based 3D orbital. So 48, it's similar, is the symmetry related. 49, this is probably a type XZ type orbital, so probably these two could be considered XY and X squared minus Y squared. This would be something like XZ, YZ, and probably DZ squared may be higher in energy. So we can try to search for it, and these are other types of orbitals. So that's one of the things we can do. We have already visualized geometries and we have visualized some orbitals. We can go, if we go back to optimization frequencies and optimize geometry, we can show the molecular orbital energy diagram. So for example, we can go to there's the alpha and beta orbitals. So we can see here the energies of the occupied and unoccupied. We can directly calculate orbital energy differences. So by default, the HOMO-LUMO orbitals are chosen, and we can change the units because atomic units, which are hardly are not what we are used to. So for example, we can go to wave numbers and we can calculate the energy differences in wave numbers. So now that we see that the HOMO-LUMO gap, the beta HOMO-LUMO gap is around 12,000 wave numbers, which would make the transition to be probably in the near infrared, if I'm correct. If we go and choose the alpha, HOMO and LUMO, the energy difference is much greater, is 34,000 wave numbers, which would be approximately 600 nanometers, if I'm correct. No, sorry, 300, around 300 nanometers. So this is more information that can be obtained. I will also show there are different things that can be just by picking atoms. For example, we can see the distance between these atoms. We can display with different colorings. Different predetermined visualizations. Some of them are very colorful. So I have my own display. So all this can be customized. So I can clone a scheme. I can edit this scheme and change common properties, atom properties, colors, lightning, shining. For example, carbon, which I have many, I can make it much more shiny. Oh, it's too shiny. There are different options that can be played with. The coordinates are also listed by going to the tab coordinates, and the format can be changed. So for example, some programs use numbers, the atomic number, to describe the atoms. Also the coordinates in the ORCA format can be used, and in angstrom or Bohr units. Images can be saved. For example, well, I will show you now how to save an image with a different file. So now what I opened is the spin density cube file that I have generated. The molecule information is still in the cube file, but now I don't have access to all the vibrations and the orbitals. It's just a file for a spin density. So if I go to show isosurface, I can see that the spin density is localized in what is a type dz squared iron orbital. So the contour value for the spin densities, or for the electron density, also usually have to be lower than for atoms, for orbitals, because the density, be it a spin density or an electronic density, is the sum of squares of orbitals. So therefore, if you use a certain value for an orbital and these values are lower than 1, when you square those numbers, you usually get smaller numbers. So the spin densities usually are plotted in lower contour values or iso values than the orbitals. So 0.001 is a good number, but also a larger number could be used. So we can see here that most of the spin density, it is located, is a positive spin density. Red means positive. We can change those colors, of course. Is located mostly in a dz squared type of orbital, but there's a great deal of polarization of the ligand spin density. So basically there's a negative spin density on the ligands and a positive spin density on the iron. So the total of that spin density would correspond to 1 net ampere electron, which is what we put in the calculation. So with file, save as, we can save the different options. We can save the structure as XYZ. We can save the image, choose some different formats. I press save, and I will save it as spin density CP2 plus. So that is all for now. I hope that this was more or less useful to start using the programs. There are many other programs. Avogadro is also can do most of these things. although I prefer ChemCraft for analyzing results, but of course Avogadro is free, so that's a big advantage. So thank you very much. Please leave comments if I can explain anything in a more detailed fashion, or I can re-explain something that was not clear. Thank you very much.